Hello? Oh my god. FOA is starting? Oh, okay. I need my puzzle. Where's my puzzle?
ChatGPT can be used effectively. Oh my gosh, sorry.
FOA starting now.
Bye.
It's time for Foundations of Algorithms. I need to get my studies to over.
I'm really looking forward to my military queue of the university.
Me too. I can't wait to get rid of these hot desks. Oh my god, FOA is starting.
What? FOA is starting? I should go get my parachute.
I've got to step my crypto watch.
Wait, it's time for FOA already. Let me get my cat.
FOA is starting. I've got to go meet the teaching fellows.
Welcome to Foundations of Algorithms.
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 I'm Izzy.
I'm Alan.
This is Tracy.
My name's Lenny.
Hey guys, I'm Violet.
My name is Enda.
I'm G1.
This was my favorite class I've had so far.
You're going to learn so much that will be so useful for your career.
It's going to be a really awesome semester.
Hope you enjoy the subject.
And remember,
Algorithms are fun.
Algorithms are fun. Algorithms are fun.
algorithms are fun.
Good afternoon, everyone, and welcome to Foundations of Algorithms. I am so excited to see you all. Yeah, you can give a round of applause. So, though not all of you are here today, there are more than 450 students enrolled in this subject. And they do represent the diversity of the entire university, not just of the Faculty of Science. In fact, there are 6 degree programs represented here. Do we have a Dominic in the room by chance? No Dominic? Well, Dominic is our student from the Faculty of Fine Arts and Music, enrolled in drawing and printmaking. And over the course of the rest of the semester, I hope to hear what all the rest of you are enrolled in, what all of you are doing. It's going to be an incredibly diverse cohort. Some of you might go on to do physics, some of you might be commerce students, pre-med, whatever it happens to be. There are all these exciting ways for you to take the skills you will learn in this class forward into whatever direction your career goes. Now, beyond just you, there are a whole lot of people that actually make this happen. Among them are our 10 teaching fellows. Teaching fellows, do you want to stand up, those of you that are here? And can we have another round of applause for them? And Tracy, do you want to just give everyone a microphone to say hi, the name quickly? Hey guys. It takes a second to load, but...
Hey guys.
There we go.
I'm Tracy. Nice to meet you all.
Yeah, I'm Alan. Excited to be part of your computer science journey.
I'm James. Really nice to see you all here today.
I'm G1. Nice to meet you guys.
Hey, I'm Alex. Excited to see you all here.
Hey, I'm Enda. Looking forward to meeting a lot of you.
Thank you very much. And along with our teaching fellows, we also have these wonderful 4 first-year fellows who you will meet in the first-year CIS Learning Centre over in Melbourne Connect. This is where we expect you to go get help in a drop-in way throughout semester. So we have your staff that you'll see in your workshops and your tutorials, and your staff that you'll see in the first-year centre. We also, for the first time, have a production associate. Rithik, do you want to give everyone a wave? Rithik is here to be helping us with our wonderful multicam setup, and behind the scenes as well we have Marty from the university who's been helping us out with the production setup. Not sure if he might already be gone, but he helps us with all our technical issues and makes this whole thing come together. Along with myself, we also have another principal subject coordinator, and this is John Jong over here. Can I have a microphone again?
Hi everyone, my name is Chen Zhongqi. I am an academic within the School of Computing Information Systems together with Shannon. I'm going to run the subject together with Shannon for this semester. You probably wouldn't see my face a lot. I'll mostly run the subject behind the scene at the backstage. But you will see my name in the assignments, in exams, and all this. Really excited. Look forward to a wonderful semester with you all guys. Over to you.
So also a couple words about myself. I'm a lecturer in the School of Computing and Information Systems, where John Jong is an associate professor. And also in my spare time, not that I have that much, I've also been a teaching fellow for Harvard CS50, which is where some of the ideas that are through this class, and as well as a couple of the slides marked with a duck, come from. So feel free to get inspired not only by our material, but when you go on your own learning journey and looking at the material of the many other great introductory computer science instructors out there. But one thing that I want all of us to focus on is our goal for the semester. Now, all of us come from different kinds of places. We might have different levels of experience with computing, different goals for what we want to do. And so figuring out the reason why we're in this class in the first place is kind of important. So to help us think that through, and to at least tell you what my goal for the subject for all of you is, I'm going to turn to the professor who teaches Harvard CS50, Professor David Manley.
And as you'll see in the coming weeks, as you write your own code and solve your own problems, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And it really is all about that delta, whether you've programmed or not, just getting something out of a class like this. And if it does take time, and if you do feel those frustrations, but you simultaneously eventually feel that sense of accomplishment, that just means it's all working. And indeed, hopefully, all the more worthwhile and gratifying ultimately as a result.
This is what I want all of us to think of today. Where you are, think about it a bit like woodworking. If you've never done woodworking before, it would be absurd to think that 12 weeks later, you'd be a master woodsmith. If you've never played piano before, you're probably not going to be playing a Beethoven piano concerto at the end of week 12. What really matters is where you are today and where you are in 12, 14, 16 weeks relative to where you started. So I want you to fix today in your mind, look around you, look at all the other people here, remember this moment. And remember, when you come back in 12 weeks' time, think of how different you'll be. So what are we actually talking about in this class? We've just introduced our staff, but it's time to actually take a look at what we're doing here in the first place. So this is really what we're doing, the art of efficient problem solving. And the word efficient here is really, really important. There are lots and lots of ways out in the world to solve any given problem. But if we don't do it efficiently, we're missing something. And we'll talk a bit more about what that means pretty soon. So here's the CS50 duck for the couple of slides that I've taken from there. But our basic model for problem solving is going to be something like this. We have an input to the problem. It might be some information, such as the details of the students in the class, the number of cities in the world and their locations. And our goal is, depending on our particular problem, to get some sort of output. So for example, if it's the name of students in the class, I might want to get a listing of all of you in order of first name so that I can help memorize them more efficiently. And that's as well something I will try and do as much as possible during this class, is get as many of your names down as possible, though I think with so many of you it's going to be a bit of a challenge. And then what we have in this black box here is we have all of our different algorithms. So for any one set of output, there will be a lot of different black boxes that we can use, a lot of different ways of solving the same problem. So I'm going to need our very first volunteer of the semester. Can I have a microphone, please? And Sonica, because you've already made the mistake of letting me know your name, well, you're going to come down to the front. Can we have a round of applause for Sonica, please? So, take that. So Sonica, how many people are there in this room?
Too many.
Too many. Okay, can you count them, please? Okay. I'm waiting.
It's going to be tough.
Count them out loud.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17,
Louder.
19, 20, 21, 22, 23, 24, 25, 26.
Okay, stop. That's enough. You're not good at this. We'll hold our round of applause. I'm not particularly impressed with Sonica's attempt at a counting algorithm. Does anyone have an idea of how we can improve what Sonica was doing? Okay, Trace, can you run a microphone down to the back over there? And give us your name as well and what you're studying. It's on, just takes a second.
Oh, okay. Oh, yeah, there we go. I'm Jack, studying computing. You could take a small sample size, say in the corner, and then just apply that to the entire lecture hall to get a rough estimate of how many people there are.
So that's one really good idea. We could use an estimation technique. So I could say how many people are in this corner, therefore how many people are in the room. Any other ideas? How might we figure out how many people there are in the room?
I have one way.
You've got an idea?
Yeah, like if we fill up the empty spaces, we can have an average idea of how many people are sitting in one row and then just multiply the...
That's a really good idea. And in fact, you came across something novel that I hadn't thought of before. Given that this room is more full than empty, we could just count the empty spaces and then subtract that from the total number of seats of the room, and that would give us another algorithm. But we're going to do something a little more interesting. So I want everyone to stand up. Everyone stand up where you are. And in your head, I want you to pick the number 1. Fix the number 1 in your head. Okay, everyone got that? Now I want everyone to find a partner very close by, and one of you is going to sit down, and the person who remains standing, add the number that the person just gave you. So you say the number in your head to the other person, and one of you two sits down. So go ahead and do that now. Okay, if you've done that once, then we should have now half the room sitting down. So if you've given your number away to someone, one of you two should, instead, if like you added 1 and 1, one of you should have the number 2, and the other person should be sitting down. Okay? So half of you should be sitting down now. Now I want all of you who remain standing, find a new partner, add your numbers together, and one of you two sits down and the other one keeps the number. Okay, let's have a little bit of quiet just for the last few people so you can shout it out now. Guys, quiet down. Okay, what have we got? What numbers do we have left? 51. 51, okay. Add 51 to whatever you got. Okay, you can sit down. 18. You got it? Yeah. And 73. Okay, how many people are in the room?
I'm getting 146.
146 is actually a reasonable number to have gotten. So we don't know exactly how many, because we might have messed up our algorithm, our programming's gone wrong somewhere along the way. But this is an example of a more efficient algorithm. By pairing people together, we didn't have to count everyone individually. Now, because we're not computers and we're in a messy room, this actually took us perhaps a little longer than if we'd just gone through and counted, but you get the idea. So can we have a round of applause for Sonica over here? Thank you, and we'll take the microphone back. So really, I wouldn't be here and you wouldn't be here if the universe were infinite. After all, for any given problem, we could just try every possible solution and keep going and leave our computer running and running and running and running until we found the right answer. As long as we have a way to check it, we're fine. So many problems in the world can be solved in this way if we only had a way to test every solution. But the real world's not like that. In the real world, our computers are limited. Hopefully your computers are a little faster than mine. This has been chugging away since '87, and I mean, I'm getting old and the computer's getting old and we've got a lot of problems left to solve. But given that even my fancy new M1 Mac over here is limited, that's going to determine the types of problems that I can actually solve using this. So does anyone know what the most valuable share in the world is right now? Not by growth in the last couple of weeks. NVIDIA. Yeah, what does NVIDIA make? Shout it out. Graphics cards. And why do we need graphics cards? Crypto maybe a few years ago, but AI is really the answer. So when we're doing AI, we're doing these vast, vast computations, trying to get large amounts of statistical information out of very big data sets. But we wouldn't really need to worry about this if we had infinite time and infinite computing power. And the reason that NVIDIA is such a valuable company is because they're doing things more efficiently. So that's what we're going to try and be learning. And on that kind of notion, let's look at another historical example of a problem that required a lot of computing power. So again, I'm going to go to you guys. Who knows what this is? The Enigma machine. So who put up your hand if you said that? Trace, can you run a microphone over? Come on, you're a runner. I know you can do this.
Put this on Strava today.
Okay, name and what you're studying.
I'm Blake, first year science.
Yeah, so tell us a little bit more about the Enigma machine. What is this?
It was a cryptography machine used by the Nazis in World War II to encode messages, basically, so that other people couldn't read them. It was a very complex machine that required a lot of other machines to break it.
Yeah, so Blake's got it right. This is a code-creating machine. And essentially the way it would work is you would press one of those buttons after plugging in cables all around it. And if you type in the letter A, the letter G might light up. And if the letter G lights up, that's what you write down and send to your Nazi counterpart on the other side. You might then type in the letter L, and then the letter Z would light up, and then you'd write down Z on your keypad and send it over to the other person over Telegram. And so this was a mechanical way of trying to hide the messages.
In post-World War I Europe, secrecy between paranoid nations becomes paramount. The growth of international commerce creates a need for companies to keep their information secret from competitors. Germany's Arthur Scherbius develops the Enigma machine as a means of keeping those business transactions secure. It works by generating an electric current when a letter key is pressed. A number of moving mechanical parts then scramble the path of the current, producing a different letter each time the key is pressed. The Enigma machine is about to become the German Army's most powerful code-making weapon in World War II.
So for the next half of today, I want you all to put on your code-breaking hats. And while I don't have a code-breaking hat with me, don't worry, there will be costumes for some of the rest of semester. But we've just received, John Jong and I have got this transmission in from the university. They said they're going to do something terrible to the students, but we don't know what. So we're going to need to figure out a way to break this code. So one way to think about how we might start breaking it is looking for patterns in the message that we just received. So maybe are there repeated letters in here which would give us a hint about what the Vice Chancellor is planning to do to all of you? Well, in order to solve that problem, first we're going to have to solve this problem. How can we efficiently, meaning before all of you graduate, figure out all the places in the message where there is a repeated sequence of L letters? So for example, if I have the string, and a string is just a computer science way of saying a sequence of letters. If I have this string fat.rat.eat.bat.cat.eat.fat.rat. And I'm looking for all the places where there are letters being repeated. So let's look for where there are at least 7 letters being repeated. So can anyone see where there is a set of 7 letters being repeated somewhere? A and T. A and T is only 2 letters long. Is there a 7-letter sequence? Yeah. So fat.rat is 7 characters long, and that is repeated both at the start and at the end over there. Thank you very much. What was your name? Jeha. And you are studying? Computer science. Okay. So we're going to write a program, and I'll show you this program in a second, to try and solve this problem. And what we want the output of the program to be, we want it to tell us all the locations where there are these repeats of 7 letters. So I'm going to switch to Ed over here, where I have set up some programs to actually do this. And you don't have to worry about the details of how these programs work for right now. We'll cover them again later in semester in a little more detail. So I'm going to go into my folder, find repeats, and don't worry about the commands again. All of this will start to become understandable to you a little later on. And I'm going to run my program find repeats 0, which is the first one. In computer science, we like to count starting with zeros instead of ones. And I am going to look for all the repeats in this file called wandp.txt. Now, if any of you are really good at word games, you might have a guess. WandP stands for war and peace. So if I open up that text file, I'm going to open up, but I'm going to run my find repeats. It's going to tell me all the locations in War and Peace where there are repeats of at least 7 letters long. War and Peace is a really long book. Okay, I'm not sure this is going to finish by the time all of you graduate. Okay, we've got a bit of a problem. Okay, so I'll tell you at least what I was doing there to try and find the repeats. This was my algorithm, and I've written it in something we call pseudocode, which is a mix between English and computer code. It's just a way of describing, in a way that's understandable to someone who in this instance speaks English, kind of my procedure, the same sort of instructions that I want the computer to follow. So let's take a look at this. The first thing we've obviously got to do is we've got to read in the sequence of letters that we want to look for repeats in. If we don't do that, what are we even starting with? Okay. Now, the next thing we do is we're going to have 2 loops, and we call these nested loops because one is inside the other, and we're going to look through all the different characters, and I'm going to represent the set of all the different letters by n. So that is going to be as many letters as there are in my book. So if my book has 100,000 letters, then n will be 100,000. M in this instance is going to be the length of the repeat that I'm looking for. So I could look for every time that 3 letters are repeated. I could look for every 4 letters are repeated. In the demo, we were looking at 7. And so 7 would be my M here. So N might be 100,000. M might be 7. OK, so we're going to go and increment I. I is going to start at 0, and then we'll go 1. I will become 2. I will become 3, all the way up to 100,000 minus 7, which is... Come on. 99,993. Okay, so that's how many times that loop is going to run. Okay, but now for each time that we increment that I, we're also going to do something else. We're going to set another variable, j, and that's going to keep track of something else. And j is going to start at whatever I is currently plus 1. So let's say that we have this string rat.cat.eat.fat.rat.cat. I don't remember the exact one, it doesn't really matter. And so what we're going to want to do is we're going to want to keep track of two things. We're going to want to keep track of the letter that we're up to looking to see, is this the string that's repeated? So let's call this I. And then we're going to have another thing that we're keeping track of, and we'll call it j. And j is essentially going to be answering the question for us, is the location at which j starts the beginning of a new repeat? So if I put my j there, let's say we have a repeat, we're looking for repeats of 3 letters. I points to the 3-letter string rat, and j points to the 3-letter string at dot. So we're asking, is the place where j is where the repeat of the thing where I is? So that didn't work. Okay, so let's move j along 1. That's t.c. Okay, that's still not a match. Okay, so let's move j along 1 more. And that's going to be .ca. Okay, that's still not helpful. And we're going to keep doing this process over and over and over until j gets along to here. And now the 3-letter string that j points to is also rat. And so we have a match. And this is the basic idea behind our algorithm. So let's go and look back at the description and see if we can make sense of it from this perspective. So for j equals I plus 1, this means the repeat, the second time that it appears, must be later than the first one, because if we start again at where j equals I, then we're just going to find the same repeat that we started off at. That doesn't make any sense. We want to look for the same sequence of letters starting at a place that's further along. And we go from that point all the way to n minus m. Why don't we go all the way to the very, very, very end of the string? Does someone have an idea? Where's Trace in the microphone? Coming behind you.
Because at that point, we'd overflow the end of the string.
Yeah, so if we're looking for a repeat of at least 3 letters, and we're looking starting at the second last letter, there's obviously no way for us to find a repeat of 3 letters because there are only 2 letters left. There's not going to be a repeat there. So that explains why we're only going up to the end of the string minus a couple of letters. And then what do? We compare, let's say where m is 3, we compare 3 characters starting at the start of both of those places in the string. So we start looking at where I is and look for 3 characters, and we look where j begins and look for 3 characters, and we compare each of them one by one. So 1, 2, 3. If they all match, we found a repeat. So if all m characters are the same, then write an output line. But this was our really slow algorithm. Let's check back on it. So this method is correct, but it's not efficient. It's not going to work well when we're doing bigger strings than just at.fat.cat.rat, which all of you could find the repeats in if I just gave you a couple of minutes. So you didn't even need a computer for that in the first place. So we haven't really improved on what a human can do with our algorithm 1 looking at such a small string. We're going to want to do something more interesting and more efficient so that we can actually solve this problem and figure out what the dastardly vice chancellor has been planning all along. So this is going to lead us naturally to the question of asking, okay, we've created an algorithm, just how good is it? There are a whole lot of different ways you could think of to measure it. What are some of the ways we might think of to measure how good an algorithm is? So I've got one on here. What are other ways? How might you test how good your algorithm is? Yeah, in the middle. The speed at which it processes the data. So if we have a lot of data coming in, how much of that data can we get through, and at what speed does it run through? Anything else? Trace, over here. Also, name and proposed major. James, okay, and computing.
So we could also look at the amount of computer memory it takes.
The amount of computer memory it takes, so that's kind of this question here. And we could also look at like the time at which we start and the time at which we finish. And that gives us at least one other idea on a real computer of how efficient our algorithm is. So the question that we're really going to ask in this class, for the most part though, is if I double the input, will I need double the memory? Will I need quadruple the memory? Will I need double the time? Will I need quadruple the time? If I add n units to the size of my input, so if I add n extra letters to the end of War and Peace, will the amount of time go up by n seconds? Will it be n squared seconds or something even bigger than that? This is a really good way of describing the behavior of our algorithm. Now, it's not going to tell you whether your computation will finish by the end of class or by the end of semester, because this is asking about the relative rate of growth. That other question of what is the actual time at which is going to finish is important, and we will look at it at a number of points in time in the class. But as computer scientists, this is often the question that we tend to ask first. This gives us at least a more mathematical description of the behavior of the algorithm. The notation that we're going to use to describe this sort of behavior is called big O notation. And from now up until the end of your computing career, which is hopefully many decades in the future, you'll hear about this and be asked about this. So if you're doing programming interviews, this is one of the things that they will probably ask you about. We also call this asymptotic analysis. And the reason is because we care at the asymptote, if we go all the way along and keep adding more and more data, at some point that's going to give us a picture, it's going to give us a graph. And if we trace out the shape of the graph, what kind of graph is that? What does it look like? So this is a line, and that would be a growth of a factor of n. If we add n letters to our problem, it's going to take n more seconds or n units of memory more. So we would call an algorithm that has this kind of behavior an algorithm that is part of the set of algorithms that run in big O of n time. Now that's a big mouthful, that's a lot to say. So we'll just say it's big O of n, that algorithm. It's not super precise, but it's good enough for us. We're computer scientists, at least in this classroom, and the maths department can throw tomatoes at us after class ends. So we could also imagine another version of this algorithm which grows proportional to n on 2. So if we add n letters to our problem, it only takes n on 2 extra seconds. So if we add 10 more letters, it only takes 5 extra seconds. Now, because we're computer scientists again, and we'll get more to this in a few different weeks, we're probably actually not going to care about that divided by 2. What we want to really know is the shape of this graph. Because, I mean, what's a couple of seconds between friends? I mean, we know that the behavior is roughly going to grow proportional to the size of the input. So we could chart out along that line and figure out, okay, if I add 5 units, then if we add, 10 letters, we'll only add 5 units of time to the amount of time that it takes us to solve the problem. But we're on the hunt for more efficient algorithms. We might look for an algorithm that, for example, grows as the log of the size of the input. So let's just imagine that there's a base 10 there, and I add 100 units, 100 characters to my input. How much time do I expect my algorithm to go up? How much extra time? Yes?
2 seconds.
2 extra seconds. What was your name?
Adam.
Adam. Yes, so we're now going up. We're increasing the amount of time it takes by the log of the amount of extra information they've given us. So this is if we had an algorithm that did that, that would be a really big win, because for every additional bit of input we add, the amount of time that it's going to take us extra is pretty slow. So we're doing pretty well if we have an algorithm that's coming in at big O of log n. So one of the things we're going to discuss in this class over and over is there a better algorithm? And when we say, is there a better algorithm, it's not one that'll take it from 10 seconds to 5 seconds, although that's a nice win. What we really want is something that'll take it from like 100 seconds or 50 seconds down to 2 seconds. That would be a really, really big success. So why was our algorithm so slow? Can anyone see a flaw with what I'm doing here? Where am I wasting effort? And that was, remind me your name again?
Jack.
Jack.
You're just sort of brute forcing your way through every single character in the text.
Yep, that's true. So I am going through every character in the text. Do you want to pass it on? We'll hear from someone else. Where am I wasting effort here? Okay, you found someone? Yep. Good.
Because the algorithm is going through the sequence multiple times, so it's just wasting a lot of data memory.
So we may be going through the sequence in some sense multiple times, but that might be necessary. Is there anyone who can see something where we're definitely wasting effort?
Maya, pure math, sorry, I'm losing my voice. You're not, like if the first character of the two strings are different, you don't need to test the rest of the characters because you already know it's not going to match.
So Maya has hit upon a great point. Maya says that we're wasting effort because we don't actually need to, if we're looking at sequences of 3 letters, we don't need to look at all 3 letters to know that they're not a match. So let's go back to our example here, and let's move this back here. So if I were to run my algorithm, I starts at rat and j is at dot, and what our algorithm is doing is it's checking, is r the same as a? Is a the same as t? Is t the same as dot? But that's really a waste of effort. If we're looking for repeats, as soon as we check if r is equal to a, and they're different, then we should just stop. We shouldn't go on to check that the next a and t are the same, because we already know it couldn't possibly be a repeat if the first letter doesn't match. So that gives us our first improvement to the algorithm. So before we figure out what our improvement does, let's figure out how long this algorithm takes. So how many different combinations of i's are there? How many different i's are there? Someone back there, yeah. N minus m, and which of those numbers is bigger? N. Is n much bigger than m? Well, in the examples we've been doing? Yeah, and if we're looking for repeats of a string, the chances are that the size of the repeat that we're looking for is probably going to be small compared with the size of the overall string. Who here is doing physics? Can I have a hand up for all the physicists? Okay, physicist over there, take the microphone. Okay, what do physicists normally do when you have a really big number minus a pretty small number?
Approximate.
Approximate, okay, so what is, in this case, n minus m, what's it close to?
N.
N, yeah. So for our purposes, we're just going to ignore the m. The m is small, the m is titchy, we're not going to care about it. So let's say that the outer process is going to run n times. Okay, what about the inner process? And we'll stay with the guy before. I need your name as well.
Zane.
Zane, okay. So J starts where I was. How many times is that going to run?
Well, depends on the value of I.
Okay.
Yeah.
But you're a physicist.
Mm.
So let's make some approximations here.
I see. What's gonna run approximate, like on average, n over 2 times.
Okay. And is 1 over 2 a big number or a small number?
Not really that big a number.
Yeah, we probably don't care about it. So how many times is the inner one gonna run?
N.
N, okay. So we're throwing away all the small numbers. Okay, so if the outer one runs n times, and the inner one runs n times each time that outer one runs, so what do we get?
O of n squared.
We get n squared. We're multiplying n by n. Now, while this wasn't perfectly accurate because we threw out a few numbers here and there, this gives us a sense of at least what's happening there. So now, what about our innermost instructions? We're saying compare m characters. How long does it take us to compare m characters? How many comparisons are we going to do?
J comparison. M comparison.
M comparison. So if we have 3 letters to look at, that's 1, 2, 3. So we get n squared by m. Oh, that's looking a bit awful. N squared by m individual character comparisons to run. This is like, if we remember our graph from before, we had like our beautiful n, we had our n on 2, we had our log n. We're pretty unhappy now. Can we have a round of applause for Zane, who helped us through with that analysis? So this is good from like a very high level perspective, kind of to characterize our algorithm's behavior. But it turns out if we actually look inside the machine, if I were to open up my processor and see what are the actual machine instructions running when I run my little C program, you'd see something like this. This is assembly language. Those of you who are in the more comfortable workshop, which you can hear more about in the Lecture 0 recording, you might actually see some of this. And these are closer to the instructions that the computer is actually running, as opposed to the code that you will see that's a little more human-friendly. But this code up here is the code that's necessary to do one comparison. And if I count how many lines, there are 6 in this picture, but really it takes approximately 10. 6 is close to 10, so that gives us 1 order of magnitude extra comparisons that we'll need to do that if we actually are keeping track of the exact number that we'd need to keep track of. So let's actually do a rough approximation here. So let's say n is 1,000. We have a string of 1,000 letters. We're looking for repeats that are 10 characters in length. Then n squared by m is 10 to the 7. My laptop can do about 10 to the 10 operations on each of its cores, but for our purposes, we're talking about a program running on just one core of the computer. So if we do the maths, 10 to the 8 on 10 to the 10 yields 1,000th of a second. So actually, this seems like pretty good. My laptop can solve this problem. So all of you can go now. We're done. We've found our algorithm. But as you might remember, when we tried actually running this on something a little bit bigger, this really wasn't so good. So when n is 1,000,000 and m is 100, so when we have something like the size of a few War and Peace repeated a few times over, and when we're looking for pretty long repeats, then n squared by m equals 10 to the 14. If we add that extra power of 10 for the number of machine instructions, that gives us almost 30 hours to solve this version of the problem. So not really good. Now, why might I not care about this? Why might I not be worried? So a lot of you were talking about NVIDIA before. How might NVIDIA be able to help with this problem? Already heard from you. And it was, name again? Jack. Okay, not Jack. Sorry, someone else. What's your name again? Adam. So, sorry, we're going to hear from there. Yeah, go ahead.
Using GPUs, you can run multiple things at once.
Yep, and have GPUs gotten faster over the last 20 years?
Yes.
A lot?
Significantly.
Do you have an idea?
Not numerically.
Many, many orders of magnitude. So you might say, well, we probably don't need to worry because just wait 2 years, and in 2 years, according to Moore's law, which is a law of computing, the power of our computers will roughly double in 2 years. Now, why is this a bad bet? Just if you know anything about Moore's law, why is this a bad bet? Yeah.
Because we're reaching the limit of the size of physical components for GPU manufacturing.
Yeah, we probably can't double the amount of speed that our computers have every year infinitely because there's only so small that we can shrink our individual components, so much power that we can pack into a small amount of space. Our computers can't double in improvement every 2 years forever. I mean, that'd give you a beautiful exponential curve, but the universe just doesn't permit that kind of thing. So unfortunately, we can't rely on Moore's law. And in fact, already Moore's law is starting to break. We're already hitting this limit. So, however, let's say for a minute that we do still have Moore's law. Even with Moore's law, we would have to wait 20 years to get the improvement from where our algorithm is now to the point where it's going to do that same 1,000th of a second solution. So, I forget who it was. It was Zane? No, Zane or Josh or someone said one of the things that no, it was Maya. Sorry. Yeah, now I remember. It was Maya over there. He said, well, we're actually just wasting a lot of our effort. We can do much better on average because we don't actually need to compare every letter with every letter. We can stop early as soon as we find a character that's not matching. So here is our new algorithm. Do the same loops as before, but this time compare at most m characters, and you stop as soon as you find a discrepancy between the two. So this is much faster, but Zane, we're going to go to you again. What's the running time of this algorithm? N squared times... So how many character comparisons do we have to do? Just run it over, Trace.
So we're doing n.
Speak into the microphone.
Wait, so we're doing n in the I loop, n in the j loop.
Yeah, but how many characters do we have to compare on that? Compare at most m characters.
Oh, at most m characters, yeah.
Yeah, so you're a physicist. Yeah. At most m characters is probably pretty close to...
M characters.
M characters, okay. So in the eyes of our physicist, at least, it is much faster, but it's still...
M squared.
It's still n squared m. So we haven't actually made an improvement in the shape of our graph. So we haven't solved our problem. In practice, this is going to be faster. Yeah. You had something you wanted to say? Ooh, we could do some fancy things. Yes, we could use some data structures in order to solve our problem, but don't spoil week 10. So for today, we will introduce a data structure today. Don't worry, you'll get a little teaser, but we are going to revisit this problem in much more detail a little later in semester. So even though it's n squared m, Zane might not be happy, but the rest of us should be at least a little happy, because on average, we're only checking k letters, and k should be much less than m. So even if we're looking for repeats of 20 letters long, it would be silly to say that most of the time we're actually going to be doing that checking of all 20 letters, because we know most of the time we're not going to be finding a repeat. If you pick a random place, you pick 2 random words in War and Peace, they're not going to match. So most of the time we're only going to compare 1 letter, which means k, the number of letters that we actually check, is in most cases going to be much, much smaller than m. So Mr. Physicist, again, I know I'm picking on you a lot. What's a more realistic approximation for the running time of this algorithm? M squared?
Or n squared.
N squared. So most of the time, we're probably just going to do 1 comparison, which means that a better approximation for our running time is going to be n squared. But we've now got this conflict between the worst case running time of our algorithm and the average case running time of our algorithm and the expected case running time of our algorithm. So we're going to have to explore this notion a little more, not only in this class, but as you get into later classes, about how to accurately characterize algorithms mathematically such that we know what's the worst possible case that will happen, but also realistically kind of what do we expect to happen. And this is going to be one of the interesting themes that you will revisit from today onwards again and again and again. So when n is 1,000,000, we're still going to need to do at least 10 to the 12 comparisons, which is at least 1,000 seconds, but that's a lot better than our 30 hours. So maybe we have actually solved our problem a little better. And that is what I would call your welcome to computer science. So we will stop for a break in a couple of minutes, but a few notes on what we've just done. So what we've done wasn't engineering. We did a little bit of engineering there. I had a program that I'd written, but it's about something more fundamental. We're actually discussing facts about the nature of the universe, the way that problems are constructed. When we're doing these kinds of mathematical analyses of the relationship between an input, an algorithm, and an output, we're actually doing something much more interesting. For any goal you have, there'll be a variety of approaches you can use to solve the problem. And it's actually a question about how the universe is constructed, mathematically and physically, about what approaches will actually work, and how they relate to the amount of time, the amount of energy, or better, the number of steps that something will take. So from here on out, you're going to be thinking also about trade-offs. So what can I maybe do to increase the amount of memory that I use, or the size of my computer, or the speed of the processor, or the way that my algorithm runs, in order to achieve these faster and faster running time speeds. So if you have a very small computer with a very limited amount of memory, a fewer boxes to play with to store all your information in, then you might have to write a different algorithm than someone with the latest and greatest NVIDIA GPUs. So this is already happening when we're training very large models. The people who train very large models have to make different trade-offs than the people who train those same models but only have access to limited resources. And again, as you go through, this will be one of the really exciting things about computing. To put it simply, one of the most important trade-offs that we have in computing is a trade-off between space and time, hence our kind of beautiful space-time-ish graphic over here. To put it simply, the more information you store, very often, the less you have to think, which unfortunately has happened to far too many of my past students. They have tried to store too much and have not done enough thinking. But I know that will not be the case for all of you. Further, there's another trade-off you could make. You could actually do some of the work ahead of time, store that in your memory, and then recall that work that you've done at a later stage. So using these tools, we can improve on our algorithms and improve on them contextually based on the kinds of situations that we know we'll have. Either a different type of computer or more time to prepare ahead of time, and this will lead to our design of different algorithms. And with that, we will take a few minutes break. Let's meet back here at 2:45 for the second half of today's class. Thanks, everyone. See you in 5. Welcome back from the break, everyone. Hopefully now you're excited about computer science. But for now, we're going to talk about one of the next lessons that we have to learn in order to solve our problem. And this is the lesson of abstraction. This is something you're going to learn again multiple times throughout your computing journey. But it's one of the key ideas of both computer science and Zane of physics. The idea of taking a problem and zooming in or zooming out to get different features that might be useful, to hide different aspects of the problem, to hide different parts of the code we've written, in order to enable us to think about aspects that we might not be thinking about if we're always focusing in too small or focusing in too big. So what do I mean by abstraction? Well, one thing we can think about as an abstraction is a data structure. Now, what do I mean by data structure? This is a theoretical, like an idea in your head of a way of relating different kinds of data together. Now, again, that's too abstract to make much sense of, so we probably need an example. A good example is files in folders. So I have pre-prepared a whole bunch of folders on this computer here, and now where did I put my screwdriver? I'm going to open up this computer and I'm going to pull out all the folders one by one. Now obviously that's not going to work because files and folders are an abstraction. If I look hard in here, I'm probably not going to be able to find the files and folders. Even if I would peer deeply, gaze longingly into the computer's memory, there aren't actually any files and folders in there. What they are is they're a way that we've chosen to represent relationships between different magnetized regions inside the computer's memory. And so this is the same thing that we're going to do when we talk about more complicated data structures. We're going to conceptualize relationships between different parts of the data. We'll still store them on a normal hard drive, on a normal magnetic hard drive, but just this point of envisioning the relationships and using those relationships to provide structure to our information is going to actually enable us to solve far more problems than we could do if we didn't have that abstraction. If we just thought about data as linearly arranged as magnetic regions starting at the very beginning, at the first centimeter of the hard drive, all the way to the last, well, I guess the hard drive's a little small. The first micrometer of the hard drive all the way to the last micrometer of the hard drive. So here we have our files and folders that aren't there. But what our goal is going to be is to design the right data structures, to conceive of the right abstractions that will allow us to design the right algorithms to solve our problems more efficiently. And I had a bunch of people coming up to the front with me with suggestions for ways that they thought we might do it. I heard one correct suggestion, but there were lots of other interesting ways of people thinking about, like, how could we arrange the words in War and Peace such that we would have an advantage next time we tried to look for repeating letters. And this is what we're going to do for the next little bit. So I'm going to introduce our first data structure, other than files and folders in the class, and this is going to be called a suffix array. Now, this is not a very common data structure, but it is useful for our particular problem that we're looking at. So this is what a suffix array looks like. Here we have our string from before, fat.rat.eat.bat.cat.eat.fat.rat, and that we're going to say that begins at the very first letter. That's what our string is if we start at the beginning. What happens if we start at the second letter? Well, then we'd get at.rat.eat.bat.cat.eat.fat.rat. What if we start at the 28th letter? Then we just get .rat, and all the way to the 31st letter, where this time I'm counting starting with 1 instead of counting by 0, but you get, it's the same kind of notion. We're talking about different entries in our table, and our 31st entry is just that letter T. That's the last character in our string. Now, just like this, it's probably not given us much of an advantage. We do have this nice property that every possible suffix of the string, every possible ending of a subset of letters in the string is represented, assuming that we're preserving the order. So everything from rat.eat.bat, etc., all the way to just that letter T, which is our one character suffix, they're all in our table. So there are a few rules to this new structure, this new arrangement that I've just done. So all I've actually done here is I've arranged it in what we call lexicographic sorted order. Lexicographic just meaning that we're using a lexical sorting, which is another fancy way of saying words and letters. So this is going to be our alphabetic version of sorting it. So you can see all the way at the top, we have at, which is the first. If we were to arrange all the different suffixes in alphabetical order, at would be first. That T is somewhere in the middle, because T is somewhere in the middle of the alphabet. And we're just going to say that dot comes after Z in the alphabet as a matter of convenience. It doesn't really matter as long as you're consistent about these choices. So for example, a question mark, it's not clear if that becomes before A or after A, but as long as we set some order and stick to it, this approach is going to work. And then we have our letter R in the middle, the letter F before that. So we've got a structure, and it now has a few rules now that we've sorted it. So all the suffixes, all the possible suffixes are present, just as before. It's lexicographically sorted. Each suffix is matched to the place where it begins in the string, because you'll see, even though I've shuffled the rows, I've kept track of the original position. And the original position was just where it started in that string, where that suffix started in the string. And then we have this additional rule, which is that the strings most similar to a given entry are on either side of it. Now, I'm going to pick someone random this time. Trace, can we have a microphone over here with the red on your t-shirt? Okay, what's your name?
Rania. Rania. R-A-N-I-A.
Rania.
Yeah.
Lovely. And you're studying?
Data science.
Data science. Okay. So given that for any string, its two most similar strings are the ones immediately above it and the one immediately below, what could be a strategy for us to find a repeat?
You could go from like the middle, and if it's one above and one below, you could just like...
So maybe let's start at the very beginning, a very good place to start. So over at the very top of the table, let's say we're looking for repeats of 2 letters. How can I find my first repeat of 2 letters?
You could go to the next row and see if it's also there.
So tell me a bit more explicitly. What do I start? What am I looking at first?
We're starting from the top, which is just A and T, and then you'd go to the next row and see if you could find that sequence of letters in that part as well.
Do I look for it anywhere?
From the start?
From the start. That's going to make sense. Okay, so I see AT and AT. Okay, I've found a repeat. What do I do now?
You go through the rest of the row.
Okay, I keep going, and when do I stop?
Until you can't find AT anymore.
Okay, now that helps us find AT. Are there any other repeats of 2 letters long? And how can I find them? So we got all the way down to where that number 2 is.
Yeah.
Right? Okay, so now let's go to the next line.
Then you do the same.
Same thing, okay. BA doesn't match CA, okay.
Yeah.
What do I do?
So then you go to the next row.
Okay, CA and EA.
That doesn't
match, okay. Help me out here. Okay, CA and EA doesn't match. What's the next thing I look at?
Sorry, I'm not quite sure what you're asking.
So there's CA and EA, and you've said they don't match, and our rule is to go to the next line. So help me do that. What's the next 2 lines? So we are 17 and 9, and now we're looking at 9 and 20.
21.
Yeah. Okay, so compare the first two letters of those for me.
EA.
EA and?
And EA.
EA, okay, so you've done it. You've helped me find another match. Okay, so we've done that now. We go EA and FA, that's not a match. FA and FA, we've got a match. Okay, let's go to the next one. FA and RA, not a match. RA and RA. Now we have a really efficient way of actually finding every single repeat. Can we have there was Rania, right? Yeah. A round of applause for Rania. So now we actually have a really efficient way of finding every single repeat in the entire set of strings. And we've done this by creating a data structure. Our data structure hasn't actually added any new data into our problem, but just by arranging things differently and by doing this little exercise at the beginning, where we've put all the suffixes into a table and sorted them, we now have a really, really fast way of finding all the different repeats in the problem. So we've talked a little about how to find the repeated strings, and this is what it looks like in pseudocode. So the first thing we do is the same thing as before. We've got to actually read in our string. Once we've done that, we create our suffix array table. And so the way we do that is we just start at the first letter and put that suffix in. We go to the second letter and we put the suffix in from the second letter. We go to the third letter, we put the suffix in from the third letter onwards, etc., etc. So that's our first, next two lines over there. Our 2 lines over there. Once we've built our suffix table, our suffix array, we now need to sort it so we get that nice lexicographic sorting. So that's over here. Don't worry about the details of the syntax for the time being. And then we have our procedure that Rania helped us with right before, where start at the top line of the table, go to the last line of the table, and compare at most M characters, which was Maya's innovation, which was to give us that idea of, well, we don't need to look at all the characters, just wait until you find the first one that doesn't match. Okay, so what's the running time? And I want someone else to answer here. In the Hilfiger t-shirt over here. So hint, sorting k items takes on average k log k. That's your hint. Over here in the white, yeah, put your hand up so Trace can run it over to you.
So the sort is k log k.
Yep,
and
but we don't have a k in our problem, right, do we?
That's
if there are k items. How many items
would be
do we
the
have?
length of pi, so it's n minus m.
Yep, and thanks to Zane, we know that we don't care about m.
So it's n. And
so we have n items, and how long does it take to sort n items?
N log n.
N log n, but there's a trick here. Unfortunately, our items are strings, which means that we're actually going to have to do, in order to sort them, we're going to have to look at the entire string every time. So we're going to actually get n m log n as a result, because we're going to have to do an extra comparison. We're going to have to check the whole word and not just the start of every item. Okay. So how long does this take? The very top bit.
N.
It takes n, so we're adding n things into our table. Then we do our sorting, which we just said takes nm log n. Ugh, should pick different letters next time. And then our last thing, where we're running from the table top to bottom, how large is our table?
N.
N items, and so how long does it take to look through n items?
N.
N. So if you have to put it all together, what do we get? So we have
2n plus nm log n.
Okay, so that is mn log n is going to be the ultimate running time. Why do we not care about the 2n? Zane, I'm going to throw this one back to you. It's small in comparison. So mn log n is going to be bigger than our 2n. And we know that because as long as m is larger than 2 and log n is larger than 1, there's no possible way for 2n to be larger than mn log n. So that's going to be our biggest term. And in this case, the exclamation is for excitement, not for factorial. But that is going to be the overall behavior of our algorithm. And does anyone remember, Zane, you probably remember what our algorithm was before our last one? It was n squared m. So this is a big improvement. We've now got that nice kind of log behavior. Admittedly, we have to multiply it by that linear line as well. But we've made a big improvement. Okay, So let's actually run this algorithm and see what we get. So that was find repeats 0. Let's look at Maya's find repeats 1 with War and Peace. Maya, it's not finishing. Okay? No response. I guess your algorithm wasn't that good after all. Okay, so Rania's algorithm. Let's give that one a try. Sorry, I missed your name for a second there. Oh, no find repeats. Find repeats 2 is missing. So I'm going to quickly make that. And this syntax will also be revealed to you soonish. Okay. Oh, I don't think this is Rania's one. Let me remember what find repeats 2 is very quickly. Oh no, this is the suffix array. We're good. Okay, so find repeats 2, War and Peace. If I leave that running for a minute, it should actually finish. But you can see, even if we compare it to before, where we kind of got up to the 36,000th one after leaving it running for a while, this one is already up in the hundreds of thousands of repeats just by leaving it for a few seconds. So maybe we'll come back to that one in a minute, because War and Peace does have a lot of repeated letters. But let's try and do an empirical evaluation of, let's try and calculate exactly how long this would take based on our running time, on our formal running time that we got to before. And I'm still watching that running to see when Rania's one is going to finish. Hopefully it won't take too long. So for n equals 1,000,000 and m equals 100, that's approximately 4 times 10 to the 9 iterations, which is about 10 to the 10 divided by 10 to the 10, which is a running time of 1 second. So now let's see if we actually give all of these a run on various different sizes. We get this beautiful table showing just how dramatic the difference is between the different versions of our algorithm. So for 10,000 letters, it doesn't really matter which one you pick. All of these are going to be so fast as to appear to be pretty much instantaneous. Once we go to 100,000 letters, you can see the one where we were wasting all that work is already going to take about 1.5 minutes, whereas our method 2 with a suffix array is going to complete almost instantly. And even when we get all the way up to 100 million, our suffix array one is actually still going to complete. And then with our n equals 1 billion, we can still make estimates of how long it'll take to run, even though we don't have time to do it in lecture. It would take 3 months for our naive find repeats 0 to finish it. 3 millennium for it to finish. 35 years for our optimized for Maya's version. And then only 24 months for our final suffix array version to finish. So I think now where we're done, we've solved the problem. There's nothing we can do better, right? We're done? No? Why aren't any of you leaving? What, you want me to do better? Fine. Fine, I prepared for this just in case. So there are a couple of things we could do. So we could come up with an even better sorting algorithm, because you'll remember that when we did the suffix array, the thing that was the slowest was that sorting process. That was the mn log n. So we could come up with a better sorting algorithm, which I did earlier, and it got about 50% faster. So then it's 50 seconds to sort 50 megabytes, which is about 10 million words. So that's a few hours of work to actually write this code. Or I could write an algorithm that makes the suffix array altogether in a better way. So maybe I could double the speed of it again. This would be a few days worth of work for a seasoned algorithmatician and programmer. And you do get better algorithmic complexity that way. But you're still going to come across some limitations at the end of the day. There's only so much we can get from doing it this way. So we can still do better. So let me run my over here, and I'm going to now run find repeats 3. Ooh. And now you can see that within an instant, it's already up to hundreds of thousands. Location like, can't even see that, like 300,000 in there. Yeah, within a couple of seconds. So that's doing pretty well. You're still looking at me. I'm getting a bit uncomfortable here. Okay, fine. We can still do better. So now instead of writing a program in C, I'm going to actually write the machine instructions. I'm going to write it into assembly code. And then hopefully this assembly code will be really, really fast. I'll eke out a little bit more performance. My program will run You're still looking at me. Oh my God, fine, fine. Okay, does anyone know what this is? Yes? Yeah, this is a multi-core processor. This is in fact an Intel 10th generation microchip under an electron microscope. And you can see all these, in these individual cells, all of these are different cores of the computer. So if you were to open up a modern computer, you don't just have one processor in there, you'll have lots of processors in there, and each processor can do many different tasks at once. So this would be great, but our algorithm unfortunately doesn't parallelize. We haven't written it in a way that it can nicely be split up between all the different cores. So with a bit more work, I can finally come up with method 4. Method 4 is going to use more disk space. It's going to be more complex because I've got to figure out a way to transmit it to different cores. So it's not actually going to be as fast if you just have a single core computer. However, with parallelism, we're now going to be able to run our overall problem, solve the actual problem that you came to me with, this thing about the Vice Chancellor's evil plot. We're going to be able to solve that faster because now we can split it across multiple cores, or even better, we could split it across multiple computers. I could distribute parts of this task to lots of different computers, or if I was Jensen Huang, who is the CEO of NVIDIA, I could fire up a whole ton of graphics cards, and graphics cards have thousands of cores on them as well, and each of them could solve a little part of my puzzle. So version 4 that I've actually written, and you can take a look at, can process 100 million strings in 7 days. So that's not really that great compared to our other methods, but you can solve it in 10 minutes spread across 1,024 processors. So this gives us kind of the lesson that problems can be solved in a whole lot of different ways. The right way that gives us the best, beautiful, theoretic, algorithmic complexity is not always going to be the one that actually leads us to solve the problem the best way. It depends on what your actual problem is and your framing and your context. And that's going to be one of the key takeaways from the entire class. And I know I've spoilt it for you early. Like you'll leave today, you'll say, look, I learned everything I need to know. He taught it all to me standing on one leg. That actually is true. As long as you remember this lesson, this is what's going to carry you through all the different possible jobs you could have in computing. Figuring out what the problem you need to solve is, what the context is, and what the resources are available to you is actually one of the largest parts of solving any real problem in computing. So what will your algorithm actually be used for? And this is one of the things that I think makes computer science fun, because it's not just about that theoretic algorithmic complexity. If you want to be a theoretician, I think that's fun, I think it's beautiful. If you want to be an engineer tackling real problems for a company that has financial constraints, you can do the same type of exercise. It's just the optimizations that you're going to make will be different depending on your situation.
I'm designing a machine that will allow us to break every message, every day, instantly. I'm just a mathematician.
Sometimes it is the people who no one imagines anything of, who do the things that no one can imagine.
And so now, finally, after all that, I think it's appropriate to say, welcome to Foundations of Algorithms. But, unfortunately, this is a university class, which means we want you to be able to actually demonstrate something useful at the end of this, and to actually show us what you've learned. So, we're going to have you make some of these algorithms in the real world. Now, how do I make an algorithm in the real world? I'm hearing some whisperings from over there. How do I make an algorithm? Some of you at least have had a semester of experience already. How do you make algorithms? Code. Okay, so we've got to actually write some code. So from here on, for the next little chunk, we're going to talk about how to write code in the programming language that we're going to use for this semester, the C programming language, which is one of the older programming languages out there, and probably the first programming language that was created that's actually amenable to being learned by ordinary humans like you and I. So C is what we call a compiled language. That means when you write the code, you're going to first send it to a second program that we'll call the compiler, and the compiler will take the code that you've written according to a certain specification of what words you should write and how you should write them, and it will turn it into this assembly code. There's also another paradigm of programming called interpreter code, and what this is where you actually need a second program to be running in order to run your first program. So Python, for those of you who've programmed in Python before, to run a Python program, you type in Python space the name of your program. And so what happens inside is the computer runs the Python program, and then the Python program reads your code in, and then the Python program itself runs the code. C, on the other hand, you actually run this conversion process ahead of time by using the compiler. Now, there isn't really a strict difference between the two. You could say, well, an interpreted program is just doing compilation on the fly, like the Python program is ultimately creating machine code as well. And that is true, but for our purposes, we're going to think of C as a pretty strictly compiled language. And so the goal is both to write code that makes your compiler happy, code that is correct, and code that makes me happy. And as long as you achieve all three of those goals, you'll be good for the semester. So one or two notes about the history of C. C was largely promoted by Brian Kernighan and Dennis Ritchie, who are two very famous computer scientists. Probably Dennis Ritchie is closer to actually having designed the language, but the two of them together published a book called K&R for Kernighan and Ritchie called The C Programming Language, which was the book that I actually learned the language from. It was published in the 70s and is still a good read, even though some of what it teaches has now been superseded a little. But hearing all this history stuff is a little abstract, so I thought you might want to get something a little more direct.
Hi to all the students in Foundations of Algorithms at the University of Melbourne. I'm Brian Kernighan. I teach computer science at Princeton University in the United States. I wrote the first book on C along with Dennis Ritchie, and I helped build some of the early Unix tools like the awk programming language. I hope you're all enjoying learning everything there is to know about algorithms. Good luck with the rest of your semester.
The Zoom ended there, but that is actually a message recorded for your class from one of the creators of the C programming language. So I hope that you appreciate that. But now it's time to do what is traditional for any Introduction to Computer Science class, which is Hello World, our very first program in the C programming language. So I'm going to now go over to my Ed window, and this is going to be the tool that will at least start you off using. And this is similar to what programmers in the rest of the world would use. We're also going to introduce you to another program within which to write your C programs called VS Code, but for the time being, feel free to at least get started using Ed while we all get over our teething problems getting things set up on our own computer. So I'm going to be running a number of commands here to help me get set up. Don't worry if you can't follow along with all of them right now. There will be chances for you to get your hands dirty during the tutorials, but for now, we'll just go along at a slowish pace going through our very first C program. So, what's the difference between Clang and GCC? So if you're on a Mac, nothing. Clang is, when you type in GCC, that's actually Clang doing the work behind the scenes. Clang and GCC are two different programs that both give you the option of converting code that you've written in C to machine code, what we call the compiler. Now, because they were written by different groups of people, they've both got their different quirks. I personally prefer using Clang because I think the messages that it gives you when you've done something wrong are a little clearer, but GCC in some ways is a lot more standard and is used for a lot of common things. So there are people who argue that GCC is good to use. In class, you can use either as long as your code works. But yeah, that's a slight note on the side. Okay, so let's make our first program, and I'm going to do it in this demos folder here. I'm going to create a new file, and I will call it helloworld.c. Now, .c isn't anything special. It doesn't transform the computer magically into understanding C code. All it is a way for us to remember or to indicate to other programs that the text inside this file is probably going to follow the rules of the C programming language. So let's start writing. And don't worry if some of this is Greek to you right now. It'll be a little easier as we go on and start to explain more and more of the program features. So there we are. That's it. Our very first completed C program. You'll see it has a few features. We've got something called main. And main seems to, it evokes images of that being the central part of the program. So if that's what it's doing for you, that's correct. That's where our program is going to start. We have this printf thing. Okay, so printing, many of you will know that from Python, but that's our command to make something appear on the screen. And then we have return, which we'll talk a little bit more about when we talk about functions. So returning seems to mean it's giving something back to us. So let's give this a run now. How do I run it? So I am going to choose one of my two compiler programs that, forgotten the name again. Jack. That's what I thought it was. Shouldn't second guess myself. That Jack told us I'm going to go into my terminal and I'm going to run a command to convert this text file where I've just written some text that follows some rules. And I'm going to convert it into a C program. So I'm going to run my command clang. And now I am going to type the name of the file. And I called the file helloworld.c. And I'm going to just press enter. OK, it didn't seem to do anything. Let me look in my folder. Let's see what's here. OK. There's this file that wasn't here before, a.out. OK, I'm going to delete that. I'm going to run my clang helloworld.c again. Oh, it's back. OK. Well, what is a.out? That doesn't make much sense to me. It says executable, though. OK. So maybe I will try run this file. Now, the way that we're going to run our programs in a Unix system, which is an early operating system that many modern operating systems are built on, the syntax for running it is going to be a dot and then a slash and then a.out. Oh, I guess that a.out is the program. Now, a.out is a pretty bad name for a program, especially we're going to want to name something a little more memorable. So let's go back to our clang command, and I'm going to give it another option. So I'm going to write some extra text on this line, and I'm going to write -o, which for clang specifically and also for GCC, tells the computer, this is what I want you to name the output file, the file that you produce. So we're going to call the output file hello world. That seems to make sense. And now if I look in my directory, I can see it's created hello world for me. So let's try running it, /hello world. There we go. Our program is working. OK. So what are some other features of our program that we might care about? So there's this funny include line here, and we'll talk a little bit more about this when we talk about libraries. But unlike some programming languages, C doesn't really come with very much built in. It doesn't even come built in with a way to write things to the screen or to get input from the user. So instead, we need to tell our C program where it can find code that other people have already written that does those things. So in this case, our function printf, which produces output on the screen, that's contained, or the details of how to get it, at least, are contained in this file, stdio.h, which stands for standard input and output.h. And by using this line here with this syntax, we can tell our C program there are going to be things that I do in my program. There are going to be functions that I use in my program that are somewhere else, located somewhere else on the computer. They're code that someone else has written before, and I want you to bring that into my program when you compile it. And there's a very complicated process that some of you in the more comfortable class might get to discuss a little bit with your teaching fellow about how that process works, of how to find and collect these different bits of code from across the different parts of the computer. Okay, that explains that. Now we have this other feature that we see at the end of all our main lines in our program. At the end of all the lines in the computer where we're actually doing something meaningful. And that's a semicolon. I don't like semicolons that much, so I'm just going to delete that one. And I'm going to remake my program. Oh no, error. Expected semicolon after expression. And then it's put a little icon here and a little semicolon says, oh, I think you're missing a semicolon there. So in languages that some of you might have played with before, you'll have this experience where your program won't run if you have too many spaces, or you don't have enough tabs, or it's not formatted well. C doesn't have those rules. Instead, the way that C denotes that one idea has finished and another idea is beginning, or another command is beginning, is by having semicolons between them. So let's make my code really ugly all of a sudden. I'm going to do all of this. Will my code work? Let's give it a try. My code still works just fine. So this gives us an indication of why we might actually want the semicolons. Because if I remove the semicolons, my program now doesn't know how to separate these two ideas. Is return part of this printf thing, or is it part of something separate? You could imagine it even more clearly if I was starting to use variables. And then let's say y equals 2. Right now, without the semicolons, this really doesn't make much sense at all. Okay, so that code is not going to work. That code's not going to be useful. That is one of the things that you will find many times as beginning programmers in C. Forgetting the semicolon will upset the whole thing. Now, the other thing I will also throw in as a bonus hint for those of you getting started in workshops is one of the most common errors I see students make. Any guesses? Just shout it out. Using semicolons? No. This is a really obvious error that you would also face if you were using Microsoft Word. Not saving. Forgotten again. Adam. Yeah, so this is probably one of the largest causes of help posts in our class, is people who have forgotten to save their program before actually compiling it. So in Ed, you're not going to have to do that. It saves automatically for you, which probably gets you into a bit of a bad habit. But for when you're using Visual Studio Code on your own computers, or when you're using other programs, remember to save, or you're going to run into these problems. You'll be like, why isn't my code working? I have a semicolon on every line. Remember to save. Okay, so we've said that this hello world thing, it's really just a text file. So how does our computer know to run it? Well, we're going to have a second program on our computer called a shell. And our shell is going to do the job of taking in commands that we type in on the terminal, understanding them, and processing them. So one thing we might want our shell to do is we might want our shell to convert the text file into a program. And then our shell is also going to have a way to recognize which files on the computer are programs, and then to run those files. So why couldn't I just run hello world directly? Why did I need to have this /? Does anyone have a clue of why I needed this funny syntax at the beginning? Maybe someone who's programmed before. And your name was?
Blake.
Blake.
/ is a command to run a file.
Is that?
It's a command.
So kind of right. It's command to run a file. Well, what have I got in the background here? Leave it with Blake for a second.
Yellow brick road.
Yellow brick road, which is a, what's another word for a road?
Path.
A path. Okay, so in computer science terminology, when we say a path, we have to tell the computer where to find what it's looking for. Now, if we were to just type in hello world, the computer doesn't know where to find hello world on the computer. Now, you might say, well, that's stupid. It should always just look in the directory where you are. But that could get confusing for the computer if you name your files badly, the same as other programs on the computer. So let's say I have a command called Firefox on my computer that opens up the Firefox browser. And now I'm inside a directory, and I call a text file Firefox. I'm writing poetry about Firefoxes. If I type in the Firefox command, it's going to, if I type in the Firefox command, and my computer is just always going to look in the current directory, then it'll read my poetry instead of opening my browser. And that's probably a confusing behavior. So instead, we have a sequence of characters that we type in, which tells the computer where to find the program. And in this case, the syntax dot is just a short way of writing the current directory. So we don't have to type out the full location of the current directory every time. And then our slash after that is going to be indicating that we want to go inside the current directory, and inside the current directory there is a file called hello world. So I can demonstrate this a little further. So right now I'm in the demos folder here, and I'm going to use another command, cd, change directory. And I'm going to use another bit of shorthand, the double dots over here, and that's going to move me out one directory. So I can see I'm now inside lecture 1. Lecture 1's over here, and demos was over there. But hello world still exists inside the demos folder, and I want to run it. So what could I maybe type to get to hello world, even though it's not in the current directory anymore, without changing? Where's Trace? In the middle, or James? This one's in the middle. I'm going to shout it out. Yeah, it's good to have it on the microphone so it's captured.
Could you write the name of the file like demos / and then hello world?
So let's try that. So let's start from the current directory. Hold it. Keep holding the microphone. So remember, how do I talk about the current directory?
With a full stop. Full stop.
Okay,
slash.
full stop. Yep.
Yep. And then / and then demos.
Demos.
Then another /, then the file name hello world.
And then hello world. Oh, and it works. Okay, can we have a round of applause? So what we're going to spend most of the remainder of today on is basic input and output and basic instructions in C, just so you can get started as quickly as possible with actually doing some of the programming. Now I know you're like, but we were just learning about algorithms and it was so exciting. Yes, and algorithms are exciting, but in order to make the algorithms, we need to know just a little bit more programming in order to get us to the point where we're actually able to implement things like find repeats. So let's talk about basic input and output. And I'm going to write another small program for you which gives you a demo of how you would actually do this. So let me close off some of these files. And let's make another program, and we're going to call this one io.c, just to stand for input-output. There's nothing special about the name. And now I have it opened up over here. So I'm going to include standard io.h, because I'm going to want to get things in and out, and I need that printf function. And I'm going to write the same thing as I did before. This is going to be mandatory text that you'll need to include in any program to get it running, but again, we're not going to worry about it too much for the time being. And now I'm going to want to create some variables, some space in my computer to store the information from the user. I'll manipulate it a little, and then just print it out. So let's go ahead and create a couple variables. So I'm going to create an integer x, an integer y, and let's create a double z. Now, a double we'll talk about a little bit more later, but it's essentially the way we represent numbers that have decimals in them. And in C, integers cannot have any decimal points. So an integer is a number like 1, 2, 3, 4, 5, or 0, or -1, -2. Now, again, if you're a mathematician, you might start getting angry at the way that computer scientists abuse numbers. You're just going to have to live with it for the time being. And then a double, that's going to be a number that has a decimal point somewhere in it. So this has created the space inside our computer for these numbers. We've told the computer, make a space for x, make a space for y, make a space for z, but we haven't actually put anything in them. Now what's going to happen if I don't tell the computer explicitly what to put there, is it's not going to bother actually putting anything there. It'll just give us some space somewhere inside the computer's memory. Now, what are we likely to see at that space? Does anyone have an idea? Who said that? Yeah, what's your name? Shah. Okay, so Shah's got it right. There's probably just going to be junk there. It's whatever was left behind in the computer from whatever used that spot in the memory beforehand. So this also teaches us another important lesson, that if you're going to use a variable, it's really important that you initialize it. You can't assume that it's going to be 0, because the computer doesn't want to waste its time setting things to 0 if you're not going to use that memory later. Instead, it'll just give you the space. This space is yours. That's for you to put all your information in, but there might just be junk in there right now. So in order to use this space, we actually have to fill it with something. So I could fill my double with a number like 2.3. I could set y to 1 and x to 77. So now I have them all initialized, and I'm going to go ahead and print them out. Now the printf function in C has some weird syntax that's a little annoying. You'll probably go over it a lot through your ed workshops and your problem sheets. I'm not going to belabor the details now. But needless to say, you have to use these special commands that start with a percentage sign in order to get it to print out variables. You can't just say print x. Why is this not going to work? What will I see on my screen if I try and get it to just print x? It'll just print the letter x. It's not going to print out the variable x. Like, it's not going to print out 77 for us, because I haven't told it to reach into that variable and print out what's inside. I've just given it a letter. So that's not going to be helpful for us. Okay. But I do still want it to print out whatever was inside x, so I'm going to use this special syntax. And because x is an integer, this syntax is going to be %d. So let's do that, and I'm going to run it. And hopefully it'll, there we go, there's a new terminal. So cd lecture 1, I'm going to change directory into demos, and I'm going to run my command to compile io.c and call it io. Now, here is one way to really ruin yourself. The computer will not prevent you from doing something stupid like this. This is another issue I've seen, and students have lost hours and hours of their projects when they type this command in and press enter. What this would do is it would tell the computer, convert the file io.c into a program and store that program in a file called io.c. I'm going to press enter. Uh-oh. io.c contains binary data and cannot be displayed. So I've overwritten the English version of my code, the code that's written in C, with a compiled version of the program, and I've overwritten all my hard work. Thankfully, this is not my first time at the rodeo, so I saved it all to the clipboard. But be very, very careful when running the compilation command that you don't accidentally overwrite your own program. So let's see if I can open it up again. There we go. Phew, my program is safe. So now let's try doing that the correct way. io.c, and I want the program to be io with no .c. Okay, I got it right this time. Let's run io. Ah, there we go, x equals 77. So this equal sign there isn't actually doing anything special, it's just a symbol that I typed in. So I could replace that equal sign with the word is, and this program would work just as fine. Okay, x is 77. What about this /n here? Let's see what happens when I remove that. Okay, oh, that's funny. Now everything's kind of mixed together. Let me try put it back, and then I'll put in hello world again. Okay, still not looking good. What if I take away this /n here and put that /n there? What does it do? Ah, can anyone see what the /n is doing? Yeah. Next line. So if I want to print a new line, I need some way of telling the computer what you should output is another blank line for me to get to the next line, and that's \n. And it turns out if you type in backslash followed by any one of a number of different characters, these are going to tell the printf command to print out something special. So in this case, a backslash n is a new line. Okay, so I printed out my x. Now let's see if I can print out some other things. So x is that. Let's do y is that. And I'll add another /n. And then z is, and I'll try this again. And what I'm doing here with this syntax is I'm telling the printf command that for the first percentage thing, I want you to put in the value of x. For the second percentage, I want you to put the value of y. And for the third one, I want you to put in z. Let's see if this works. Oh, it's given me an error, a warning. Format specifies type int, but the argument has type double. Okay, so what this is essentially telling me is this last %d shouldn't be a d, it should be an f. Because d is only for integers, and what we have there for z is a double. So d would only print a number without a decimal point, not with, so I need to change that. So let's go ahead. Warning is gone. Now there we have my answer. Now what if I want to change the way that, look, there's a lot of zeros in that, and that's a real eyesore. If I want to change how that looks, there are also other ways that I can modify the format specifier that you'll see in your tutorials in order to get just the output you want. So this is all well and good that I have shown you how to print things out, but our program probably isn't very interesting unless we talk about how to get things in. So fortunately for us, inside this library, standard input output, there's also a command that we can use to get input. And there are actually a lot of commands to get input that you could use, but I'm only going to show you one for now. However, be aware that if this is the only one you ever learn, you're going to have a hard time doing the assignments in this class. So I do recommend making sure that you're familiar with the other ones as well. This one is called scanf for historical reasons. And the way it works is using these same format specifiers, these same percentage symbols that we use to print things out, we're also going to use to get things in. So let's say I want to read in an integer. What format specifier am I going to use? Just yell it out. %d. Okay. And then I want to let the user enter a space. So I'm going to type in a space here, and then I want the user to enter another integer. So what am I going to type? %d. And now I want the user to enter a double, %f. Okay. What's my problem? I have a few problems. Okay, it says saved now. It says all changes saved in the corner, so I'm okay. Yeah, over there. Okay, that's another problem. I haven't said where it should actually store this information. What was your name? Tristan, thank you. Other problems? Oh, sorry. Yes, we're also missing a semicolon. So add a semicolon, it's still going to complain because I haven't told it actually where to store this information. And for now, you're just going to have to memorize that for most variables, you're going to need an ampersand symbol before the variable that you want to put it into. So I want to put it into x, I want to put it into y, and I want to put it into z. And now what's the output from my program going to be? It's definitely not going to be 77.1 2.3 anymore. Now it should actually, format specifier specifies type float, but argument has type double. Oh no. Okay, so it looks like the designers of the C programming language have done something very silly and very annoying, and they've actually made it two different kinds of ways to put in numbers with decimal points. So there's a number called a float that we won't use because they're very inaccurate, but for doubles that are a bit more accurate, you actually need to put the letter L when you're doing scan, even though it's okay to just do a plain F when you're doing print. So that's another kind of trick. It's probably an example of not the best design, but we'll go with it. We're smart folks. Okay, so let's try this again. Okay, why is my program not doing anything? Oh, it's asking for input. Okay, so I'm going to stop this program, and the way I'm going to do that is by pressing Control-C to stop my program no matter what it was doing before. And I'm going to make it a little more obvious to the user what I'm doing. Please enter 3 numbers, space separated, and then press enter. And what am I missing? Semicolon. OK. Please enter 3 numbers, space separated, and then press enter. So I'm going to enter 4, 99, and OK. So now we're getting more of what we want, but our output's still not perfect. I have these spaces here. It's not aligning perfectly. And if I look at my printf over here, I can see after the /n, because I've added some spaces, those spaces are actually appearing on the output. So let me compile it one more time. And there we go. There is our output. So how can I have avoided this frustration with this like LF and this F? How do I even know what to put it in the first place? So there is a technique that is tried and true by students from across the ages and programmers from across the years. RTFM, read the manual. So how do we go about reading the manual? How do we read the manual for C? Well, you could get a copy of the C programming language, which is honestly a pretty good resource. But on Linux-based systems, on Linux and Unix-based systems, which we've talked about are the ones we're going to be using for the majority of this semester, there's a special command to read the manual. It is the man command. So if we type in man, and I type in printf, which is the thing I want to read in the manual. Whew. OK, here I see the POSIX programmer's manual, and we don't have to worry about what POSIX means for the time being. So I did lie a little bit, and if I type in man printf, it's not actually giving me the manual page for the C command printf, because the man page applies to everything on my computer. So if I type in, for example, man cd, it'll tell me about the cd command. So if I actually want to look up something about C, I need to give it the section of the manual that all the C commands are in. So let's hope my memory is good here. Does anyone of the tutors remember what section of the manual it is? So I'm just going to try it. No manual entry for 3. There we go. It's 3. So section 3 of the manual is where all the C library commands are. Now this is looking a little bit better. Include standardIO.h, so that tells me what I need in order to make this command work. And then if I scroll down, I can see all the different all the different length modifiers and precision and all the different things that we could possibly want. Now this is, again, a lot to read through. Let's keep scrolling, keep scrolling, keep scrolling. OK, so it goes far too long. But if I eventually get to it, there I can see my, there we go, there's my F. See, it says if you want to print a double, %F. Now I don't actually expect all of you to read this manual because it's too long and too complicated. However, our friends over at CS50 have rewritten the manual for us in a way that's actually understandable to ordinary humans who haven't yet spent their lives programming. And so let's actually look that up. So I'm going to type in man CS50. And if the internet in this room is working fast enough, there we go. So now I can see a much nicer version of the man pages, which will be good for us. Now we don't have cs50.h, because that's not our class, but we do have standardIO.h, and we can click on printf. In theory, we can click on printf, there we go, and then it'll tell us all the different format specifiers we can use in plain language. And so with that, we're actually going to close out today. You now know what algorithms are, why we might care about them, how to make them more efficient, but also how to write your very first programs. So what I want each and every one of you to do today when you get home, I want you to write the Hello World program on Ed and just see if you can get it working. It's okay if you copy all the lines that I've given you today, but that's what I want you to do. Thank you very, very much. I'm so excited to have you, and I will see you all tomorrow.